A structure must be safe and serviceable, so that our design that we design for the ultimate limit state can serve with the intended purpose. For example, if we design as a bridge, so the bridge can sustain the load from the cars and so on. And also, for example, building for the school, yeah. So it can serve the purpose of learning and also any activities, for example, gathering and so on. So that is called serviceability. The most important serviceability parameter is deflection and cracking. Okay, now let's go first with the deflection. So the deflection must not exceed with a certain limit. For example, if we consider with the appearance, the deflection must not greater than L over 250. Yeah, L over 50, as you can see here, it must not greater than L over 250 for the appearance. And for the non-structural damage during the construction, the deflection must not greater than L over 500. If the deflection exceeded, you can see here there's a crack underneath the beam. Yeah? You can see here, this is the wall. It will show crack like this. It shows that we must check whether the deflection of the beam on top of this brick wall is greater than permissible. The permissible is L over 250 if we consider of the appearance. Now, actually in EC2, we have two method of, your friend just in. Okay. Okay, as I said just now, we have two methods in order to control the deflection. The first method is limiting span to depth ratios. It is stated in clause 742. And the other method is calculation of actual deflection as highlighted in clause 743. And both methods can be used, and it must the limiting span that we calculated must not exceed L over 250, yeah, for the appearance of a slab or beam or cantilever beam subjected to quasi-permanent loads. So what is quasi-permanent loads? It is actually the load that sustained by the slab. For example, the imposed load and the permanent load. The type of load will be discussed after this lecture. Okay, so the second one is that if we consider the finishes or partition, so we must consider that the L over D or limiting span over depth ratios does not exceed span over 500. Sorry, there's your friend. Okay, checking for the deflection. All right, we have seen just now we have two methods, and but in this course, I will teach you how to check the deflection using the simplest one, that is the first method, limiting span to depth ratios. Okay, so in this method, we must calculate L over D allowable is equal L over D basic. Yeah, L over D basic. Don't be confused with this one. L over D allowable is equal LD basics time modification factors. Yeah? So we have to consider many modification factors, such as highlighted here. That is the first one, modification factor due to flange, modification factor due to span, and modification factor due to tension reinforcement. Therefore, this is called allowable. It must be greater than L over the actual. This is L over the actual, meaning that the L of the beam divided by D that we have in the design. So in order to the beam safe from the excessive deflection of L over D 250 just now, this is the comparison that we have to make without calculating the actual, using the long equation. So we can consider that L over D allowable greater than L over the actual can give a beam safe from the excessive deflection. Okay, just now I've mentioned L over D basic, and L over D basics can be obtained from this formula. This formula can be obtained in your book or in the design formula booklet. So L over the basic is actually depend on the two equation here. The first equation is L over the basic K11 plus 1.5 and so on. And the second equation is L over the basic K11 and plus 1.5 and so on. So these two equation, the difference is that the first one doesn't have a compression reinforcement. This is compression reinforcement. So you can see the difference is the last part of the, yeah, not the last part, this part and this part. This is the difference between the two equations. So we have the same coefficient K, the K. Yeah. So what is rho naught? Rho naught is reference reinforcement. This is rho naught is square root FCK grade of concrete times 10 to the power of minus 3, while rho is the tension reinforcement AS required divided BD, and rho dash is the required compression reinforcement AS required divided BD. Okay, so it's stated here required. What is required? Required is the area of steel that you obtain directly from the calculation during the design. It is like when you got K and then you find Z, then you got AS. That AS that you determine is the AS required. Okay, so if your rho, that is the percentage of tension reinforcement, less or equal than rho naught, the reference reinforcement, therefore we must use equation 1, while otherwise you need to use equation 2. First. So just now I said this both equation we have K, right? So K can be obtained from table 4.1. This table give us the K for FYK 500 with a grade concrete C30/35. For example, for the first one, simply spotted beam, K is 1. Yeah, the K is 1. For end span of continuous beam, for one-way continuous slab, it is 1.3, yeah, the K value. And then interior span of beam, 1.5. Slab supported on the column, 1.2, and cantilever, 0.4. Okay, the K, the value of K. And this is the L/D basic. Yeah, L/D basic is equal 14 if the rho less than 1.5%. And concrete, if the beam has a tension reinforcement 0.5, so we get the LD basic. Let's say for the simply spotted 20. This value is obtained from the equation just now, equation 1 or 2. Yeah, depend on the rho and rho dash. Yeah. So this is example if we use C30 and FYK 500. Yeah, the value of L/D basic. So this is actually L/D basic that obtained from equation 1 or equation 2. Equation 1 or 2. So we have if your tension reinforcement 1.5%, we'll get 14, and if your tension reinforcement is 0.5, you will get 20. Yeah, this is from the equation 1 or equation 2 with K 1.0, right? Okay, this is the illustration of the figure to describe this table. Yeah, in this table we have simply spotted beam with K1 and span of continuous beam 1.3, interior span of beam 1.5, cantilever 0.4, and you can see the figure that describes the description in the table. So this is cantilever beam. Yeah. This is called cantilever. Cantilever. So if you design cantilever beam, so the K is 0.4. This is simply spotted. Yeah, everyone knows 1.0. So this is for the end span. If you have like a continuous beam, yeah, continuous. What is continuous beam? It's more than one span. Yeah? So it is continuous beam. So your K, if you consider deflection for this span, K is 1.3. While if it is interior span, yeah, we have span this side and also this side. Also, you got another span. So if you consider deflection at this span, the K is 1.5. Okay, now just now we have established the L/D basic. So now we look what is the modification factors that we need to consider. So the first one is modification due to flange. Yeah, for example, we have a T-beam here. So the top dimension, we call it as BEFF. Yeah, you have already know how to calculate BEFF, do you? and also BW here, BWeb. Okay, for this, the shape of this beam will contribute the modification factors in where if BWF, the dimension at the top here, divided by BW greater than 3, then we multiply by 0.8. If only BEFF divided by BW greater than 3, then you must multiply by 0.8. If it is rectangular, therefore it is equal to 1. Yeah, so we don't need to consider the factor due to modification of flange. Okay. Second modification is about the span length. Yeah, this is applied if the span here is greater than 7. Otherwise, you don't have to consider it. So if your length is 9, then the factor is 7. The 7 divided by 9. Right? This is the second modification. And the third modification is due to tension reinforcement. Yeah? So your provided, AS provided divided by AS required. And what is AS provided? AS provided is that the area of steel that you look at the table appendix at the back of your book divided by the required. When you calculated, we'll get AS required. So if provided divided by required less or equal than 1.5, so you need to multiply this ratio to the L over the basic. So if the value greater than 1.5, so you need to take 1.5 as the modification factor due to tension reinforcement. Okay, now look at this example. So we have the simply spotted beam here. We have a simply spotted beam with L, and we have designed this beam which resulted 2H12 for the compression reinforcement and 6H20 for the tension reinforcement. In L here given is 8. Yeah? So B 250 and D 550. So the characteristic of concrete is 25. Characteristic of steel 500. The tension areas required. Yeah, this is when you calculate, you get the AS required 1663. And when you provide the steel by looking at the table at the back table of steel, you provide 1885. And also for the compression steel, when you require you calculate, you got 200, while this one is when you provide. Yeah? So check the beam for the deflection. Is it exceed the allowable or less than the allowable? We must remember that a beam that we design must has L over the actual less than the allowable. Okay. Now look at the solution. Remember just now the most important thing is that L over the allowable must greater than L over the actual. Yeah? So what is L over the allowable? Is the L over the basic time with modification factors, and we have 3 modification here. Yeah, so let's calculate. But I have to delete first this one. Okay, so now remember just now we have 2 equations here. We have 2 equations, equation 1 and equation 2, and we need to calculate rho naught and the rho. Yeah, that's why here the solution begin with the rho. Rho is the percentage of tension reinforcement divided BD. So our required given is 1663. So 1663 divided by B and D, so we have 0.012. So reference reinforcement is FCK square root times 10 to the minus 3. So we have 0.005. So now we need to compare rho and rho naught. So our rho is actually greater than rho naught. Yeah? Rho naught here 0.005. Therefore, we use equation 2. Yeah? This is the equation 2. L over D K11 plus 1.5 square root FCK rho naught plus, yeah, here, just follow the equation. Okay, the K is 1 because this is simply spotted, yeah, the K. So from the calculation, we have 14.75. This is the allowable, the basic. Yeah, this is called basic, L over the basic. Okay, then we proceed with the modification factor here. Yeah. This is actually calculation for the modification factor. So the first modification factor is here, yeah, due to span. So since the span is greater than 7, so we need a modification factor, 7 divided by span. So you have 7 over 8 here. Okay. The second modification is that still area provided. Yeah. We don't calculate the flange because our beam is simply is a rectangular beam. So if you design rectangular beam, so we need to ignore the modification factor due to flange. So now we proceed with the tension area steel. This is your friend. Okay. Okay, so modification factor for the steel area provided is AS provided, given is 185 divided by AS required. So you got 1.113 and this is less than 1.5. Yeah, so now our allowable here, this is allowable, yeah, this is L over D allowable. Okay, this is allowable actually, yeah. Okay. L over the allowable is 14.75. Okay. This is allowable. Yeah, this is allowable. So this is we got just now is the basic span over depth times the 0.88 due to the span greater than 7 times 1.13 is due to modification factor for the tension steel. So we have 14.63. Nomor asterisk, yeah. Okay, actual span effective depth. We have the span length divided by 550, so we have 14.5. So we compare the allowable with the actual. Therefore, our allowable is greater than the actual. Therefore, the beam is safe from the excessive deflection. Okay, any question? Ya.
Nak tanya yang untuk modification factor yang greater than 7 meter, kalau dia kurang daripada 7 tu macam mana kita nak consider?
Ignore.
Oh, okay.
Yang tu hanya untuk kalau modification factor if your span exceeding 7 meter. So let's say kalau you punya span is 6 meter ke 5 meter, so you don't consider this lah.
Okay, noted then.
Okay. Ada lagi soalan?
Doktor, kalau 7 meter?
7 meter, tak ada apa-apa jugalah. 7 divided 7, 1 lah kan.
Okay.
Okay, any more question? Hamzah Bukti, are you here? Hamzah. Tak ada kan? Jani? Apa lagi tadi? Okay, tak ada Right. So we go to the next one Okay, cracking So this is the second element in serviceability limit state So similar with the deflection, cracking also must not be excessive So cracking is actually maybe due to flexural tensile stress. Remember last time when we discussed about the under reinforced and over reinforced, right? Okay, so this beam it shows under reinforced, so this is called flexural tensile crack, because it is located at the mid-span. Let's say this is mid-span, this is mid-span. Kalau mid-span dia tegak, mid-span, so this is due to bending, so flexural tensile stress. So we want to avoid this one. Sometimes cracks happen before the beam receive the ultimate load. Okay, diagonal tension. Remember, diagonal tension at the beam. Last time, diagonal tension near to the support due to shear under applied load. Crack also happen due to volume changes. You can see here, nampak ni due to volume changes. When you cast the concrete, let's say from the day 1 and day 30, you can see there's a crack, micro crack at 30 days due to the volume changes, creep, thermal, chemical effects, and also sometimes crack due to bond and anchorage failure. Last time when we consider how to get cover, the main steel and the steel and the concrete, maybe there are cracks between the steel and the concrete due to the splitting due to bond and anchorage failure. Therefore, cracking here that we consider is the cracking that must not be excessive during the service. The crack must be limited to the certain value. Okay. Friend just want to join Izam and Aisha. Okay, now the primary objective of control crack is to limit the width of individual cracks. So our intention here is not to control the whole crack. Our objective is to control so that the certain value of crack will not be attained. I will elaborate this after this. Similar with the deflection, control of cracking also can be obtained through two methods. The first method is without direct calculation. This is can be obtained in clause 733, and another is by calculation of the crack width. So here in our course, we only consider the first one. That is, we control the cracking without calculate the width of crack. Okay, we just control the spacing and also control the amount of steel. So we are now using the first method. The second method is we will calculate what is the crack width. So this second method, if you want to know more, maybe you can join the, your final year. We have a concrete, what do you call, elective, in elective course, the second one. Okay, limiting crack. So just now, our method is just to control the crack in the beam or in the slab, with a certain value. So that we have two types of crack width. The first is 0.3, as you can see here, 0.3, and the second one is 0.4 millimeter. So which crack width that you should choose is depend on the condition of your beam. For example, if you consider that your beam under quasi-permanent combination of load, that means you have loads like live loads or permanent loads. Permanent load is the load from the self-weight of the beam, and also imposed load or live load is load from, for example, from people. It's called live load. So both combination of load and it quasi-permanent. That means the load will be stay for a long time in the room. So we must consider the crack width is 0.3. For the water tightness also can be limit to 0.3. But for the water retaining structures, we cannot tolerate with the crack limit. So the crack limit will be 0 for the water retaining structures. For the building, it is 0.3. Okay, the second one, 0.4 millimeter. The second one, 0.4 millimeter. In the absence of requirement of appearance, this category is if you don't bother about the appearance. Crack will bother our eyes, right? So in that case, we must consider 0.3. If you don't bother, so you can select 0.4. This is, for example, for the exposure classes XC0 and XC1. Remember what is XC1? It is in the building for low humidity, right? And XCO is in the building as well, but without reinforcement. Okay, so as our method is just to control the cracking. So we have three methods here. The first method is by providing minimum reinforcement area of concrete. Minimum reinforcement area. Second one, provide the bar size less than the maximum bar. The third one is provide the maximum spacing of spacing that left. What is it? Ashura. Ada apa Ashura? You want to talk something? Nak cakap ke? Okay, the third one is maximum spacing of the reinforcement. Okay, so again, cracking can be controlled by three ways. The first way is that we calculate the minimum area reinforcement, and we make sure that the provided reinforcement must be greater than the minimum. The second one is that the bar size of tension reinforcement must not exceed the maximum bar. The third one is that the spacing between reinforcement must less than the maximum spacing that we will calculate. All right. The first one, minimum area reinforcement. So this is the equation for the ASV. It is equal with 0.26 FCTM divided FYK BWD. So FCTM is I have explained to you last time, yeah, what is FCTM? Concrete tensile, mean tensile stresses in concrete. Okay, so you get AS mean. All right, so B here is the BW. Although you design T-beam, yeah, you must use BW in this equation. Second one is the maximum bar size. Okay, last time we don't bother what is the maximum bar size for our beam, right? So actually there are limitations. Yeah. All this while we just consider the area and then we find the number of steel in the appendix. Yeah. Actually, you need to consider the limitation of the bar size. So from here, table point 3, it guides us what is the bar size, maximum bar size that we should use for a beam or slab. The most important thing is that we must calculate the service stress. This is service stress. This is service stress. Fs is the service stress. Since why service stress? Since we are now checking serviceability limit state, so that's why we use the service stress. Service stress is the stress that derived from the load, from the service load. Yeah? Service load. Service load is load that we use without safety factor. Yeah? So I will explain you more in the loading in the next lecture. All right. So Fs is equal Fyk. You can see here Fyk is the strength of the steel divided the factor of safety times Gk. Gk is the dead load. 0.3 Qk is the imposed load or variable load. Permanent load, variable load divided by 1.35 permanent load plus 1.5. Qk is the variable load. 1 over delta. Delta is redistribution. Yeah. This is redistribution. Okay. So for now, we assume that delta is equal to 1. Yeah. Okay, we will see later for this one. But now we just assume it is equal to 1. Gk and Qk will also, I will explain it to you after this lecture. We have next lecture about Gk and Qk. Okay, now let's say you already have the value of Gk and Qk. So we have Fs here. From this calculation here, this is the Fs. Yeah? This is column Fs. Okay, this is the column of the crack. Wk is crack. Crack is called Wk. This is crack. This is crack wave. So now we have two choices of Wk. So if you consider about appearance, so we have to consider 0.3. Yeah. So if let's say you got Fs, your value is 0. Let's say your value is 250 here. Let's say you got 270 something, 270 here. Meaning that your maximum bar must be less than 16. The value must be less than 16. So you can get here you can get the value here. You can do interpolation. Yeah? So maximum value that you must provide in the beam is between 12 to 16. So maybe you get 15. So you can round it up to 16, something like that. But if you don't consider the appearance, it's slightly higher here. Okay. Therefore, now we know that in a beam there's a condition or limitation about the bar size. Yeah? So you can refer to this 4.3. Okay. Let's erase first. Okay, the last one is the maximum spacing of reinforcement. Yeah, just now we have calculated the area of steel required in the beam. The second one is determination of the maximum bar size, and the last one is finding the maximum spacing between reinforcement. Yeah, so for the maximum spacing, we need to refer table 4.2 here. 4.2. Again, we need to calculate what is the service stress. Yeah? The service stress we have calculated just now. Okay. So again, if our value is 270, then we can get the maximum spacing between 200 and 150. So again, you can do the interpolation here, right? So that is how we can get the maximum bar spacing, yeah, for the crack control. So these three elements is to control the crack, right? Although you have designed according to the ultimate limit state. Let's say you got the diameter of steel 25, but when you check, yeah, to crack control, and you determine it must be less than 16 millimeter diameter, then you need to change from 20 to 16 millimeter. Okay, let's see now. We have the example here. Okay, let's say now we have a beam with given GK. GK is the permanent load, and QK is the variable load. Variable load, that is load that can movable load in the room. Yeah? Let's say we have a QK is 10 kilonewton meter, while permanent load is 19.6. So permanent load is the load that permanently on the beam. So the span is 8.25 meter. So the design has been carried out, yeah, with the compression steel 3H12 and the tension steel 6H20. The D is 587 with the cover 35 and the grade of concrete 30. So check the cracking for the beam. Okay, now the first criteria is that for control the cracking is calculate the AS min. The AS min here. So what is the important here is that what is the value of FCTM. I got 2.0. This you can refer to the formula here. Okay. Rotate view. Okay. So our grade is 30 right now. Yeah, 30 here. So FCTM. So our FCTM is 2.9. Yeah? 2.9. FCTK 2.0. Okay. So our value is actually 2.9. Ini actually is 2.9 2.9. Okay. And value kat sini pun jadi 221 22 2 2 1. Okay. Are you okay? Dengar tak? Nampak tak?
Nampak tak? Okay.
Okay. Tadi saya tersilap tengok ni Nanti sekejap Okay. Okay. Saya ulang balik lah Okay. So we have new AS min 221 so that H8 H6H20 1885 ni the provide, right? So the provide now is greater than 221, so therefore it is okay for control of tracking. Let's say the AS min is greater than provided here, so you must choose the AS min. Okay, the next one is maximum bus size. As I said just now, maximum bus size must be determined as well. Okay, so last time when we design, we don't consider what is the maximum bus size in a beam, right? So now we know that there is a method to determine what is the maximum bar size in a beam or in a slab by looking at table 4.3. Yeah. So the first step is that we calculate FS the service stress. Because now we are considering the serviceability limit state. So the stress that we consider also must be service stress. So service stress is equal inilah shown in the equation. Yeah, so GK QK. GK is the permanent load. Permanent load from the slab, from the beam. Is actually from the weight of concrete. QK is the variable. Variable load is like people. People will come and go in a room, so that the weight of people will be considered as QK. And delta here is the redistribution, and we assume it as 1, because we have not considered yet so far. So from this equation we have the new value. So we have 220 Newton per meter square. From the value, it is somewhere here. Somewhere here. So now we need to find what is the maximum bar size. Okay, before we determine the maximum bar size, we must also bear in mind that what is the limiting value for the crack. If we consider the appearance, so we must choose 0.3 millimeter. Therefore, the value of a maximum diameter of bar is somewhere here between these two values, 16 to 25. So the value you can get from the interpolation, and from my calculation, I got 21 millimeter. Yeah. Therefore, we don't have 25 millimeter, right? Therefore, the maximum value for the so that the provided steel diameter is the appropriate one is H20. So if you remember just now, the diameter of tension steel is 6H20. Yeah? The diameter is 20. Therefore, it is less than the maximum that allowed in the beam. Therefore, this diameter 20 is okay for the control cracking. Yeah? Next is the maximum spacing of reinforcement. Okay, I need to erase first. Okay, so by using the FS from the previous determination of bar maximum bar diameter, so now we use the same value. So it is 220. Yeah, 220 here, somewhere here, and our limit, the crack limit is 0.3. So the value is between 200 and 250. Again, you need to calculate by using the interpolation. Yeah, from the interpolation, I got 2 to 5. Right? So this is the maximum spacing between bars. Yeah? Okay. So we need to check our design just now. Is it the spacing less or greater than 2 to 5? If the spacing is greater than 2 to 5, then you need to add more steel, so that it will fulfill our intention to control the crack. Okay, we need to erase first. Okay, now how to determine the spacing for the beam, the given beam. Yeah, just now we have calculated that S max is 2 to 5. Therefore, S here, this is S is the clear spacing. Yeah, you can see from the figure, S is clear spacing between bars. Yeah, we have here from here to here and from here to here. Yeah? The spacing must be same. This one. Yeah? So we have this formula. This is not the fixed formula. It depends on how you arrange the steel in the beam. Yeah. So according to the arrangement, S is equal BW. Yeah. The BW minus 2 cover, first cover, second cover, left and right, minus 2 diameter link. The diameter of the link minus 3 diameter of bar. 1, 2, 3. Divided by 2, yeah, because we want to find the S, so 1S to S, so divided by 2. So now we have 52 millimeter. So it is actually less than S max. Therefore, it is good. Yeah, the arrangement is sufficient for control cracking. Alright, that is how we check the cracking. So, any question? Ada soalan? Ada soalan?
Belum lagi, doktor.
Belum ada lagi ya? Okey.
Doktor, For the 2 times x, where does the x come from? The part of diameter link, right? The 2 times x.
Yeah, diameter of the link. Yeah, this is diameter of the link. Sorry, forgot the thing.
Okay.